The following program is brought to you by Caltech.
Good evening. My name is Ravi Ravichandran. I'm the director of the Graduate Aerospace Laboratories in the Division of Engineering and Applied Science. I would like to welcome you to tonight's Watson Lecture, the Richard C. Biederbach Memorial Lecture. It gives me great pleasure to introduce our speaker this evening, Dr. Beverly McEwen, Professor of Aeronautics. Professor McEwen received her bachelor's degree with honors in engineering with specialization in fluid mechanics, and also a Master of Engineering from Cambridge University in the United Kingdom. She entered Princeton University as a Fulbright Scholar in 1997, where she received the Guggenheim Fellowship for Graduate Studies. Professor McEwen earned her master's and PhD degrees in mechanical and aerospace engineering from Princeton. After receiving her PhD in 2003, she pursued postdoctoral work at Imperial College London as the Royal Society's Dorothy Hodgkin Fellow. She joined the Caltech faculty in 2006 as an assistant professor and was promoted to Professor of Aeronautics in 2011. Professor McEwen's research is focused on the understanding and control of turbulence and its engineering applications. She has developed novel techniques for manipulation of wall-bounded flows for improved flow characteristics, such as the reduction of drag, noise, and structural loading, and thus improving the performance of aerospace vehicles. She has made a number of pioneering contributions to her field, and she will share some of them with us tonight. The unifying theme of her experimental and theoretical approach is at the intersection of fluid mechanics, control, and material science to investigate fundamental flow questions, address efficiency and performance challenges in aerospace vehicle design, and respond to the need for energy conservation in novel and efficient ways. Her numerous awards and honors include the prestigious Presidential Early Career Award for Scientists and Engineers from the White House and the National Science Foundation's Career Award. Ladies and gentlemen, please join me in welcoming tonight's speaker for the Watson Lecture, Professor Beverly McEwen.
Good evening, everyone, and thank you for coming out this evening. It's a great honor for me to be able to give this presentation today. It's the Biederbach Memorial Lecture, part of the Watson series. What I would like to do today would be to tell you a little bit about what turbulence is, what the history is at Caltech, and you'll see that there's a very long history of research into this area, and then tell you a little bit about what we've been doing to try and manipulate it and try and shape the way a flow moves. So turbulence is everywhere. You drove through turbulence coming here. Presumably you drove. Even if you walked, the surface layer, the boundary layer on the Earth, the passage of fluid over the Earth is turbulent for most of the day. The way your car moved was influenced by turbulence. The way the gas was transported to the gas station was influenced by turbulence. So I'll try to give you an introduction to the significance of this effect, the economic and environmental drivers to try and control it, and then some of the novel ways we've been thinking about this problem. So why think about turbulence? Turbulence is really everywhere. I'm going to focus my comments today on turbulence when it's close to a surface. As an aerospace engineer, I think about things like ships, planes, and pipelines, as you see here. So on the top, we have an oil tanker. This is one of the very large ships that moves oil around. Here's the Boeing 777 plane, one of the newest airliners in service right now. And here is an image of the Trans-European Yamal-Europe natural gas pipeline. And you get a sense for the scale here. Here's a model posing with the pipeline. So how much oil is consumed just moving these devices or this stuff around? So the tankers are moving oil around, moving people in the airlines, and the large pipelines, you can think of pipelines that transport water or natural gas or oil around the country, around the world. So in 100 million barrels of oil, these are figures from 2005 to 10, there is something like 2.1 billion barrels of oil spent or used just transporting things around the world in ships. There's 15 million barrels, 1.5 billion barrels, so 1,500 million barrels of oil spent in the airline industry. And in terms of moving things around through large pipelines, there's something like 1.2 billion barrels of oil used. And that's just in terms of pumping, moving these things around. So these are large numbers. And there was some work in 2006 with contributors from Caltech that estimated some of these numbers. But of course, since 2006, the cost of gas has gone up dramatically. So if we assume now that a barrel of gas costs about $100, and we start to think about what kind of savings we could get if we control these flows, and I should say that a large proportion of the cost in terms of the power to move these things around comes from turbulence. So in the terms of these flows, where is the turbulence? I need to explain that before we talk about controlling it. So the ship and the airline are different from the pipe. In terms of the pipe, all the flow through that pipe is turbulent. In terms of these devices that move through a fluid, so air and water here and air here, there's a very thin layer close to the surface in which the effects of viscosity or the stickiness of the fluid are confined, and that's where the turbulence that I'm going to talk about today is also concentrated under certain conditions. So to give you a sense for the magnitude of this, the 777 is something like 70 meters long, and the height of the boundary layer is of the order of tens of centimeters. Okay, so a pretty thin layer, and that thin layer is the region in which the air, the fluid, adjusts from sticking to the surface of the vehicle. We call that the no-slip condition. So the fluid right on the surface travels at the speed of the airline, and far away the fluid will travel at whatever the speed is of the background atmosphere. So the effects of turbulence and the effects of viscosity are constrained to what I'll call a turbulent boundary layer, or a boundary layer, and in this case it will be turbulent. For the 777, or for the airliners, something like 50% of the fuel burn, 50% of the drag is associated with turbulence occurring. So if we can influence that, we can really cut down on the amount of fuel that's spent trying to power people around the world. Now, what can we do? Well, under very controlled conditions in the laboratory, we can get something like 10% drag reduction, maybe as much as 30%. Once we have everything nicely clean in the lab and very well controlled. There are no active flow control devices in use in these type of settings right now. So getting that 30% drag reduction is pretty difficult. But let's use that as a rule of thumb. The aircraft industry, Boeing, say that you need at least 15% drag reduction in order for it to be an economically viable proposition to try and control the flow. So if we assume $100 a barrel and we'd shoot at a 30% turbulent drag reduction, how much would we save? The grand total is $140 billion per year, only in these categories of flow that I'm showing you here. Now, there are other categories that we could think about. They're a little less clean in the sense that there are other factors at play. So these are the ones where the turbulence is most dominant, but these are pretty enormous figures. The thing that's particularly interesting about this is that it doesn't matter how you're providing power to these devices or these vehicles. So you may have read about biofuels being developed to power airliners. It doesn't matter whether it's a biofuel or Jet A fuel. If you can save up to 50% of whatever you're burning, that's a very significant effort. And of course, there are other things that make us want to control turbulence as well. There are environmental costs and Noise also is associated, jet noise is also associated with turbulence, not particularly close to the wall. But turbulence is a very interesting field, and it's also a very Caltech field. So to quote one of the most famous faculty from recent years in Caltech, turbulence is the most important unsolved problem of classical physics. So that's a great challenge to work on as a professor at Caltech. So when is a flow turbulent? I've told you a little bit about where the flow is turbulent. Let me tell you why it becomes turbulent now. And we'll start in 1883 with Osborne Reynolds, FRS, Fellow of the Royal Society, and he published a paper, an experimental investigation of the circumstances which determine whether the motion of water shall be direct or sinuous, his term for turbulent, and of the law of resistance or drag in parallel channels. So here's his experimental apparatus set up in Manchester in England, and he has a very simple pipe flow arrangement where he controls the flow rate through the pressure head associated with this reservoir and a little valve here. Apologies for the quality of this. This is obviously quite an old figure from 1883. A little aside, many people think that this is Osborne himself, but this is actually Mr. Owens, who was the technical assistant who helped perform the experiments and obviously posed for the sketch at the same time. The pictures I've seen of Osborne Reynolds, he looks remarkably similar, but apparently that is Mr. Owens. So he was able to investigate what happened to a line of dye introduced onto the center line of this pipe as he increased the flow rate. So he increased the velocity, the speed of the fluid. And here are some sketches from his paper. When the flow is laminar, so when the speed is low, this line of dye continues in a straight line down the pipe. So this is a two-dimensional cut through a nice cylindrical straight pipe. As you increase the flow rate, you start to see eddying motion. So instead of being in a straight line, the dye starts to get mixed around. It's a very three-dimensional motion. And eventually, you start to see some kind of structure. So I'll explain a little bit more about what I mean by structure as we go on. But you can see some patterns developing in here. So what's the difference between laminar and turbulent flow? Well, if everybody in this audience got up and pretended to be laminar as you left the auditorium, you would all walk in nice straight lines with your arms by your side very smoothly out the doors. If you decided to be turbulent, you'd stop, you'd talk to your friends, you'd go three-dimensional, you'd wave your arms, you'd do a little dance, and it would be a lot harder for you to get to the doors. Things would be slower. You might get poked in the eye, et cetera, et cetera. There's a lot of three-dimensionality, a bit of mixing. You might end up next to somebody you didn't come in with, et cetera, et cetera. So that is the essence of a smooth laminar flow, very controlled, very two-dimensional, versus a turbulent flow, very three-dimensional, and capable of mixing. So a word you hear associated with turbulence a lot is mixing. So this three-dimensional motion here is capable of mixing both the momentum of the fluid, also heat, particles, anything else that exists in the flow. So Osborne, I should stop referring to him by his first name. Osborne Reynolds worked out that actually it wasn't just the flow rate that was important here, but he was able to form a group here. We call it a non-dimensional parameter. That means it has no units, just because of the combination of the terms here. We now call that the Reynolds number. And it's basically a ratio of inertial effects, so effects associated with the momentum, the motion of the fluid, and the viscous effects, where the viscosity is the stickiness of the fluid. So if mu here is the dynamic viscosity, and that is the resistance of a flow to shear. So honey would have a very high viscosity, water is lower, air is even lower. And we tend to group that as resistance to shear per unit mass. So we divide the dynamic viscosity by the density of the fluid to give the kinematic viscosity. L is some length scale in the problem. So in the pipe, it would be the pipe diameter. And U is a velocity, so the original velocity associated with the flow rate in this example. So as you increase the Reynolds number, at some point, inevitably, the flow becomes turbulent. The way it becomes turbulent is by amplifying very tiny perturbations that exist in the background somewhere associated with this flow. So when the flow rate, when the Reynolds number is low enough, the flow can damp out these perturbations. When the Reynolds number is high enough, it's a complex, fragile system that amplifies these disturbances, and things become apparently chaotic pretty quickly. One other important thing about turbulent flow is that in a time mean sense, so if I were to average this motion here, I could come out with a mean velocity profile, and that's the thing that dictates the through flow rate of a pipe or the mean drag on a vehicle, and I'll explain that a little more as we go on. But first of all, if we just take a cut through the pipe, the mean profile in the laminar case is parabolic, so it's shown by this blue line here. And in the turbulent case, you can see that it has a different shape. So this red line shows the turbulent case, and it has a lower velocity on the center line of the pipe and a much higher velocity closer to the wall. So that's associated with the mixing, this three-dimensionality of the flow, mixing high-speed fluid from the core, the center of the pipe, towards the wall. And it's particularly important because the drag, the skin friction as we call it, associated with this flow is dictated by the gradient of velocity at the wall. So you can see that for the red case, there's a much higher gradient of velocity and therefore a much higher drag. And in pipe flows typical of industrial applications, you can have a drag that is orders of magnitude higher in the turbulent case than in the laminar case if you try to get the same throughput in the pipe. So there are two ways to think about this. The first one is if I want to get the same throughput in a pipe, I need to work much harder in the turbulent case. Or if I fix the power that I want to put in, I'm going to get much less flow coming through the pipe. So you may have encountered turbulence. In fact, if you poured a glass of water from the faucet, you will know a little bit about this transition already. You know that if you turn the faucet on just a little bit, the flow comes out very smoothly. It's a laminar flow. If you turn up the flow rate, you start to see a turbulent jet. So it's not a wall flow in the sense that I'm talking about here, but you're probably familiar with this phenomenon. So now let's talk a little bit about how we observe turbulence. So as Professor Ravichandran introduced, I'm very familiar with the laboratory and field experiments in turbulence, in wall turbulence. So on this spectrum of the Reynolds number, so this is a definition I gave you earlier, here's the division between laminar and turbulent. So the work of Osborne-Reynolds sits to span both of those conditions through the transition from laminar to turbulent. And down here, I'm not going to talk about laminar flows very much, but things like blood flow, flow around bugs, birds, that sort of thing resides in that section of this diagram. As you move to the right to higher Reynolds number, you see some applications on the top here, the ones I've shown you before, and these are the kinds of capabilities that we have in terms of the laboratory experiments. So here is a wind tunnel. So rather than move a model, move an airplane through the fluid, we sit the model still and we move the air past the model. That's a lot easier to do in a laboratory, of course. This is the Merrill laboratory facility, and I'll show you some experiments in that facility a little later in the talk. So that sits now about an order of magnitude, a factor of 10 higher in Reynolds number than what Osborne-Reynolds was able to achieve in 1883, so 130 years ago. Here is a specialist pipe flow facility now. This is the super pipe at Princeton University. If you look very hard, hopefully you can't see it, there's a younger me sitting here, hard at work in the facility. And you can see, just in terms of where the applications sit, that this facility, which runs with pressurized air, so up to 200 times atmospheric pressure, at which point it's hardly air as we know it at all, that overlaps at least with the large pipelines that we see around the world. And it's getting up to the Reynolds numbers associated with commercial airliners. And this is one of the world's largest supertankers, so that's sort of in a class of its own. But we're at least closer here than we were here, and than we were in the case of Osborne-Reynolds. One other experimental facility that I'll talk about briefly is the atmospheric surface layer. So as you know, there are net winds across the Earth, and under certain conditions, they actually approximate the type of thing that we can put together in a laboratory. And of course, that's a very high Reynolds number because the scale of everything is very big. It comes with its own challenges, but these are some experiments that we did in that surface layer in 2005. So there's a span of Reynolds numbers that are relevant to everyday life. The laboratory range is up to here. You get some additional information from the surface layer. Computationally, one of the challenges associated with turbulence is the range of the smallest length scale to the largest length scale that you need to resolve or replicate in order to, with high fidelity, understand or mimic, solve for what the flow is actually doing. And that's what limits our capability to solve the governing equations exactly. In fact, the capability of a direct numerical simulation, the cost of that goes up with Reynolds number cubed. So if I double the Reynolds number, the cost or the number of operations that I need to do goes up by a factor of 8. So that's what's constraining this limit here. But it does overlap with laboratory experiments. And this is even using the petaflops machines, which are 1,000 trillion floating point operations per second. So the highest capability that we have on very simple geometries is just into the regime where we are able to access with a laboratory facility. If we don't want to exactly solve the equations of motion for the fluid, we can do a little bit of modeling. So we can say, okay, I'm going to solve the biggest things and make some assumptions about the smallest ones. And that's called large eddy simulation because you simulate the large eddies. So that gives you a much higher capability, but there is some modeling involved in there. So there is a big gap here, unfortunately, just about where some of these applications sit. And it's not just a big gap on my diagram, it's a bit of a gap in our understanding of the way turbulence works too. So you would think being able to make all these measurements in controlled facilities, we would know how turbulence behaves. It's very complicated. That's why 130 years after the transition to turbulence and the Reynolds number was really introduced in a formal way, we're still working on it. Let me show you a little bit of why. Turbulence is three-dimensional, it's chaotic, and yet structured. What do I mean by that? Well, here are some time traces of the velocity. This is actually from the surface layer, the atmosphere, and this is 10 seconds of time, and these are 4 time traces, a factor of 10 difference in height from the wall. So this one is at, you can see it says 1, so a log of the distance from the wall of 1. And so that is about 5 millimeters from the surface of the Earth. So this one is about 50 centimeters, 5 meters, and further up than that. So what do you see here? Well, you see a lot of activity. Looks like the type of thing you don't want to see when you go and have a cardiogram done, right? So there's a lot of very small-scale, rapid fluctuations, and there's some large-scale activity too. You can see these are synchronous time traces, so you can see that there's something interesting going on between about 82 and 86 seconds here. So there's something a little bit more quiescent in the signal. There's a large-scale negative excursion below the mean. So these are all fluctuations relative to the time mean. And it seems to be correlated or consistent across these heights. There's a variation in the activity of the turbulence level between these periods as well. So there's some kind of structure that you can see visually. The problem is really that as humans, we don't have the processing capability to document this and pick out all the patterns that exist. I'll talk some more about that in a moment, but there are some things that are coherent and persistent, and we call these coherent structures. Leonardo da Vinci knew about these, so here's a famous picture from one of his notebooks in the 16th century, and it's water issuing into a pool. And you can see he has these wonderfully intricate drawings, sketches of eddying motion. And if I read the translation of what he wrote in that book, in that notebook, it says, "Observe the motion of the surface of the water, which resembles that of hair, which has 2 motions, of which one is caused by the weight of the hair." So there's a downward motion here into the pool. The other is the direction of the curls. So rotating around on this, parallel to the surface. Thus, the water has eddying motions, one part of which is due to the principal current, the other to random and reverse motion. So that's a translation from Ugo Piomelli from Queen's University, reported in a paper by Lumley in '97. Da Vinci was aware of turbulence, and believe it or not, people have gone back to this diagram and actually checked to see whether he drew these eddying motions at the right scale based on what we know now, and he did. Right down to the sort of subscale and the pencil thickness. So Da Vinci was aware of this idea of turbulent motion, and he was also aware of the idea of a time mean flow and then fluctuations about that, which is the way that we consider turbulence to this day. Now, if we think about wall flows, on the right here is a sketch by Wesky of a very famous concept, first put forward by Theodorson in 52, or at least that's the paper that is cited. And this is what we call a hairpin vortex or a horseshoe vortex, for obvious reasons if you look at the shape here. So by vortex, I mean the type of structure, the line with the rotation around it that you see when you try to drain the bathtub. You see a vortex. You see it if you see a tornado. Hopefully you don't see it up close, but that's the idea of vortex. If you see images of a cyclone from space looking down, you see the footprint of a vortex as well. So it's a vortical motion, a swirling motion, and in this sketch, the flow is from the bottom of the page to the top, and the rotation is around, a helical rotation around this structure, such that there's fast flow on the top, and so flow into the board on the top and out of the board between the legs of the hairpin vortex. So the geometry gives it its name, but this is a concept that's really stuck around. It's still somewhat controversial as to how clearly we see these things in wall turbulence, but it turns out to be a very useful building block by which to understand wall turbulence. So these are coherent motions, and we mean by coherent motions, coherent structures, organized motions that are persistent in time and space, so you can see them, and they contribute significantly to the transport of heat, mass, and momentum. So they're dynamically important, and they stick around for long enough for you to see them. Of course, wall turbulence has some special structure. And I'm going to talk you through a snapshot now of the history of this and some of the different observations of turbulence that we are familiar with. And hopefully you'll see that there's a great history at Caltech. In fact, there are so many contributions from Caltech that I won't be able to put them all on the slide. So consider flow over a flat plate. So here's the plate. Here's the direction of the flow. So when I describe to my non-scientific friends what I do, I can either say, well, I study flat plates with air flowing over them. Doesn't sound very glamorous. So you have to try and use your imagination. Think back to the large things I started the talk discussing. But here's the flat plate. This is the type of thing we like to put into a wind tunnel because it's a very simple configuration. Now, early on, people understood the profile of the mean velocity, so the time mean. And remember that the gradient of the velocity down here, so here's the velocity curve, the variation with distance from the wall, y, and the gradient down here is what dictates the skin friction, or the shear stress, the drag associated with the flow. And there were contributions here, again, a snapshot, Theodor von Karman, who was the first director of the graduate aerospace laboratories at Caltech, aeronautical laboratories as they were then, 1930, Clark Millikan, second director of GALSIT, Don Coles, who's a current emeritus faculty at GALSIT. Now, there are many others on campus, so particularly if anyone is here, my apologies, I ran out of space on the bottom. So that's the mean, but the mean velocity tells us the least about what the turbulence itself is doing. So in 1967, Klein et al. Did some very nice experiments where they were able to visualize a little bit of the turbulent motion. So this is a visualization technique called hydrogen bubble visualization. So there's a thin wire. These are 3 planes. So the wire is put at 3 different heights from the wall. And hydrogen bubbles are released from the wire. It's better to start up here. You can see these nice straight lines of hydrogen bubbles, which are illuminated, so you can see where the bubbles go. Now, if there's no turbulence, everything's laminar and smooth, then these bubbles will travel in straight lines, and you'll see the same striations that you see close to the wire. Now, if we go back to the plane closest to the wall, you can see that that's not the case. So there's some very intense motion that's moving these bubbles around. And close to the wall, the bubbles get grouped into what we call streaks like this. So that's consistent with motion parallel to the wall, grouping these bubbles together. And then these bare bits here are consistent with motion out of the plane or into the plane, so wool normal motion. So we understand now, and some of these authors were able to suggest some of these ideas, we understand that there are vortices now aligned with the plate that are moving these bubbles around, and that's a very important mechanism close to the wall. If you move a little further away, things are a little bit, well, quite a lot more complex. I couldn't even really describe what those bubbles are doing in any kind of coherent way. But once you get further from the wall, you can see that there's very little activity. These bubble lines are undisturbed, and then you get some intense activity here. So with the advent of laser technology, the community was able to make some additional observations of turbulence. So here's a beautiful image where dye was introduced to a water boundary layer and then illuminated with a laser. And you can see here that the time mean, masks a lot of these intricate features associated with the edge of the boundary layer. There's what we call an intermittent edge, so it doesn't just sit at a constant height here. So the yellow here demarks the fluid that is turbulent in the boundary layer. But sometimes there are excursions of unmarked fluid right down to about half the boundary layer thickness. So you can see why now this top plane here looked relatively unperturbed, because it was mostly out of the boundary layer, and then occasionally it would intersect with one of these lumps or bulges, as we call them in the flow. We're getting some picture together of what the boundary layer actually looks like. We can go a step further with a technique called particle image velocimetry, which I will sketch out shortly. But for now, this is an image of the velocity field in a wool normal streamwise plane, where these colors show arrows showing the velocity of the fluid in that plane, so it can be streamwise or wool normal, and the colors dictate the intensity, or how fast the amplitude of that fluctuation is. So you can see it's pretty complex. If we look at the similar technique in a wool parallel plane, so about the same height as this, the arrows here show fluid that is moving slowly relative to the mean in a turbulent sense, so very complicated snake-like shapes here. And the colors show the footprint of vortices, of swirling motion in that plane. So they're dotted around. Red is clockwise and blue is, other way. Blue is clockwise and red is anti-clockwise. But there is some kind of grouping of these around these low-speed structures. And that's a feature that we see quite often. The last piece in the puzzle here is direct numerical simulation. So what's that? Well, it's been described as a forest of hairpin vortices or sea of worms, depends on how you want to describe it. But this is the output from a simulation, full simulation. Every scale is replicated. And you're seeing here the vortex structures, the swirling structures that were picked out of this simulation. And they're colored by the speed of the fluid at a different height from the wall. So if you get nothing else from this picture, it's complicated, okay? So how come we haven't made so much progress in this field? I love to cite John Sachs, very famous poem concerning the blind men describing the elephant. So these men of Hindustan, read the community, disputed loud and long, each in his own opinion, exceeding stiff and strong, though each was partly in the right and all was in the wrong. So if you imagine trying to describe an elephant, you're seeing one of these views and trying to extrapolate and understand the whole flow. Even when we have all of these images associated with the flow, it's still hard to understand what the flow is doing, and particularly to extrapolate that understanding to geometries and flows that are different from this lovely flat plate. Remember, you're using your imagination, it's not just a flat plate, but even so, to more complicated flows. And particularly, it's hard to extrapolate to higher Reynolds numbers. So if we go back to the range of scales here, I'm going to tell you a little bit about why it's hard to extrapolate in terms of Reynolds numbers. So if we consider this wind tunnel laboratory facility here, the plate that we work with is about as high as from my feet to the tip of my finger, so about 2 meters long. The boundary layer, that region in which the turbulence is confined, is about the height of a golf ball. Okay? So it's already a pretty big range of scales. If you want to understand the whole flow, you need to make measurements over that. However, it gets worse. The longest length scale we need to observe, measure, record is the height of 2 diameters of a basketball. And the smallest, this is not to scale, is a third of the diameter of a red blood cell. Okay? So we're going from something that you can scarcely see, 20 microns, up to 2 times the diameter of a basketball. Okay? So it's a pretty severe problem. It gets worse, okay? So let's now think about the world's largest supertanker, the Seawise Giant. It's actually out of commission right now, but it was 458 meters long. That's the height of the Empire State Building, okay? So if you want to simulate the flow around that, that's a pretty big simulation right there. Now, the boundary layer on that, see this little red person? That's the tallest female US citizen, Sandy Allen. She was 2 meters and 24 centimeters tall. That's almost exactly the largest, the thickest boundary layer that you would observe on this very large tanker. The longest scale of motion in the turbulent boundary layer is the height of this auditorium, 20 meters. The smallest scale is thinner than the thinnest of Sandy Allen's hairs. Okay, so you need to be able to measure, see, resolve, simulate from the thickness of a hair at least to the height of the auditorium. And if you want to understand more than just a little piece of this flow, you want to be able to simulate up to the top of the Empire State Building. So again, if you take nothing else from this slide, this is difficult. So I've told you a little bit about the economic and the environmental drivers to control flow. So it seems as though there's a lot of promise here. We ought to be able to do quite a lot. So what do we need for a flow control scheme, a way to make the flow do what we want it to do? Well, the first thing is it needs to be efficient, and you'd be surprised how many people fall at the first hurdle here. So any scheme to control a flow, to try and reduce the fuel burn or the energy associated with a vehicle, any scheme to control the flow needs to use less power than it saves. Okay? Think about it, it's important. There is some element of science versus engineering here, so even showing that you can control flow is quite a significant step forward at this point, but if it's ever going to go into application, you can't violate that first one. The scheme needs to be adaptable, so it needs to work under different flow conditions. We think about individual flow speeds in the wind tunnel, and that's a very nice laboratory setting, but of course that's not what happens in the real world. And it needs to be robust, so wind gusts on an aircraft, that sort of thing. It needs to be practical. If we have a flow over a wall and we want to both sense what's going on, so figure out what the turbulence is doing at that moment, and interact with it or alter it, in reality, most of the techniques we know right now need to be mounted on the surface. You can do things off surface, it's harder, and it tends to be less robust. So practically, we need to sense and actuate at the wall. It needs to be light and simple to make it economically viable. And the hardest bit really is that it needs to be informed. So we need to understand some more about the flow to really make this a practical idea. To quote Feynman again, there's room at the bottom. So we can make things that are small enough to interact with these smallest of scales in the flow. And here are some examples. So on the left are active dimples. So these little circles in a wafer, this is a 4-inch wafer, these guys are flat until you actuate them, and then they look like little blisters. They pop up. So if you think of a dimple on a golf ball, this is going the other way. So this is really a pimple. So dimples down, pimples up. So these are active dimples. They're one way of interacting with a flow passing over the top. But to do that, you need this pattern of electrodes. Okay, it's a very intensive manufacturing process, but you can do it. And these are a few millimeters across. You can make them smaller. On the right, that was work from Imperial College London. On the right are some sensors, nicely photographed to give you a sense of scale. These are of the order of 0.5 millimeter in diameter, or in cross-section. You can make them down to a few tens of millimeters in cross-section. These are shear stress sensors. So these are little floating devices, and as the fluid exerts a force on them to move them in plane, you get an electrical signal out from little tiny strain gauges that tell you what that force is going to be. What's the problem? Well, here's the A380, one of the largest commercial airliners in use right now. If I actually want to control everything on this airliner, then I need both actuators, there are many other options, and sensors. in a pattern, a repeating pattern that's somewhere between 1/4 of a millimeter in scale to 1/10 of that. So very, very tiny units that contain at least one sensor and one actuator each. If I cover the whole aircraft, so just fuselage and wings, I need, any guesses? 20 billion. And they need to be moving at the order of tens of kilohertz, so something like 10,000 cycles per second. To give you an estimate of how big of a deal this is, there are something between tens of billions and 100 billion neurons in the human brain, and they only have to operate at about 1 kilohertz. Okay? So this is a huge problem, a huge control problem. It's not even clear that we can make things that are robust enough to go on the aircraft or control them. And the problem with a fully controlled scenario like this is that if you fail somewhere on this aircraft, you may be doing something good up here, but you have no guarantee that what you're doing that's good up there isn't forcing bad further down the aircraft, so that the net result is an increase in drag. I like to call this the fitting the squid into the box problem. While I'm busy concentrating on this arm, there's no guarantee that this leg is not coming out of the box the other side. So if we want to do something like this, I would argue we need to understand the physics some more. So one of my favorite expressions since arriving at Caltech, and this is sometimes used in the context of trying to get Caltech faculty to meet, is herding cats. So on the left here, think of the cats as individual parcels of fluid. I want to force them to do something that I want them to do. So in this instance, get them into a pen. These cats all have things that they want to do, whether it's they want to go eat, they want to chase this lovely looking mouse, sit on the cushions in the sun. If I want to get these cats to go into this pen, I probably need at least one person to move each cat. Okay? That's because I'm trying to get them to do something that they don't want to do. So don't herd cats. Let's use a system-level approach and understand what the cats actually want to do and therefore encourage them. So if I were to move the mouse, the pillows, and the food into the pen, then the majority of cats would probably go that way. There's always one, right? So it's not a one-person job, but it's certainly easier. So the idea here is rather than use the hammer approach of these billions of sensors and actuators, I want to tickle the flow. I want to just move it slightly, make it think it's doing what it wants to do, but actually have it do what I want it to do. So to do that, we harness something that's innate to the flow. So one of the tendencies of the flow that we already know about is to respond acutely to surface roughness. So here are some examples. This is an Arleigh Burke-class destroyer in the US Navy, and here it is in dry dock. You don't get a lot of detail down here, but hopefully you can see there's all sorts of what we call biofouling here. So these ships go out to sea clean, and during the process of sailing around, they get weed and little creatures attached to them, which in my language is roughness. Okay? So the surface that was nice and smooth becomes rough. And the Navy has a categorization for the different types of biofouling you can observe. So fouling rating 30 is heavy slime. Sounds pretty unpleasant, but it's actually seagrass and lovely little creatures called sea squirts. Then higher up is fouling rating 60. These are small calcareous fouling or weed, barnacles that have a 1/4 millimeter height or less. I'm sorry, 1/4 inch height or less. So still pretty small deposits on the surface of the ship. But the cost, in terms of the additional power that's needed to power these ships because of this roughness, so the additional drag associated with the surface roughness, is $1.2 million per ship per year and $2.3 million per ship per year. Okay? These are pretty significant numbers. This is why the Navy brings, or one of the reasons the Navy brings their ships back to clean them every year. And there are something like 300 ships in the US Navy. So you can see that small roughness has a very large effect on turbulent flow. So how would we interact with that in a laboratory setting? Well, we like to abstract these ideas. I don't like barnacles in my laboratory, so we're going to talk about very controlled roughness. And I also like to have an additional knob to turn. So rather than just a roughness distribution, I'm going to allow it to change height in time. So the example I give is you think of an egg box, an egg carton. It's got troughs and crests in a very simple pattern. If you now allow those to oscillate in time such that the surface goes from smooth to the configuration that we're familiar with, that's the sort of thing that I'm talking about. So here's a little cartoon to keep you in mind of what I was saying. So very simplistic in that there's one scale in both the streamwise and the cross-stream direction, and this amplitude oscillates in time. So we call these morphing surfaces. I'll tell you a little bit more about how we make these later on, but this is how we're going to try and interact with the flow. So let me just skim through how we decompose turbulence first. So here is a velocity trace. So this is the streamwise velocity fluctuation in a water channel here in Galset with distance along a surface. So if I wanted to characterize that, again, my human brain can't really process exactly what that trace looks like. So if I want to break it down into known quantities so I can compare it with other flows, I might try and say, well, it looks kind of like that red trace as a first approximation. And you can see that that red thing approximates quite well for some regions of the flow and gets it wrong elsewhere. If I look at the blue trace, a very simple sinusoids here, that does better over here, does worse over here. But if I sum them together, I get a more complicated pattern. And you can imagine that you can do this with increasing numbers of very simple waves, so sinusoids here. And all I need to record are the amplitude of these waves, each one, and the phase, meaning where the first peak occurs in space. So there's a theory, I won't bore you with the details, but it tells you that you can exactly reconstruct the signal with the right number of samples as a summation of this type of waves. So that's great. So if I record these waves, then I can match different signals and pick out patterns that I can't pick out with the human eye. Problem is, that is a one-dimensional velocity signal. There are 3 dimensions. It's in one dimension in space. There are 3 dimensions. And I have no time information in there. So here is what the velocity field looks like at 30% of the boundary layer thickness, so 30% of the full region of turbulence from the wall. And this is the trace I showed you on the top. And it corresponds to what the velocity looks like on this line here. So this is streamwise distance, this is spanwise distance. Red here means a velocity fluctuation that's higher than the mean, and blue means one that's slower than the mean. So if the movie runs, here we go. This is time information, so each is much slowed down. So this data was obtained at 1,000 cycles per second. But hopefully you can see that, first of all, things are complicated up here. But second of all, while some features convect, meaning that the shape just travels downstream, so this peak is pretty much just traveling downstream, there's also what we call evolution, so that shape is also changing in time. So I also need to account for the time variation. So if I'm going to think about this flow in terms of traveling waves, I need to be a little bit smart. So you may be familiar with a very simple wave equation up here that says that the velocity of a wave is given by the product of the frequency and the wavelength. So here are some very simple waves. And here's a wave 1, which has twice the wavelength, the distance between peaks, that wave 2 does. If I add them together and they have the same convection velocity, I get something that looks like this. If I add more waves, I can get very complicated shapes. This is the type of idea behind acoustics. So all the signals travel with the same speed, the speed of sound. However, there's no evolution of this signal. So if I want evolution, then I need to start to consider waves that travel at different velocities. So here's one where wave 1 is traveling at twice wave 2. If I sum them, I get a signal that's evolving in time. And again, if you put enough frequencies together, I hope I can convince you that you get back to something that looks like this. So how does this help us? Well, we need to think about, extend this to have wavelengths in the streamwise direction, the spanwise direction, a frequency and time, and this is 2-dimensional, so I need to think about the direction out of the screen as well. So it's pretty complicated, but it turns out to be quite useful. So these are the only equations that I'm going to show you. They're the Navier-Stokes equations. We've known them since the middle of the 19th century when Claude Navier and George Gabriel Stokes, who looks remarkably like Mr. Owens from the Osborne-Reynolds figure earlier, separately deduced the equations that governed the motion of the fluid in terms of the velocity components in the streamwise direction, that's u, in the wall normal direction, v, and in the spanwise direction, w, and also the pressure shown here. So I'm not going to spend much time on them except to say that they're nonlinear partial differential equations, and they're difficult, particularly when the flow is turbulent, when there's no known solution. But this is equivalent to the formulation on the right. So what have I done here? Well, I'm going to write this now in terms of traveling waves. So k, n, and omega are a wave number, so the number of wavelengths in the streamwise direction in a length 2 pi. And n is the equivalent in the spanwise direction. So this tells me the length scale of the wave in 2 dimensions, and omega tells me the frequency. So the velocity that I observe in the flow, I can sum all these traveling waves. They interact through this bubble at the top, which produces to me a forcing here. And this is a format that's quite familiar to controls engineers. We call these orange blobs transfer functions. And what that means is this velocity here is the result of a forcing that's acted on by this box here. So if that box just contains a multiplicative factor, and say it's 1, then what I see here is equivalent to what comes in. In general, it's not 1. It can have an amplitude, it can have a phase, it can move this distribution around in space. But this formulation is quite powerful because it tells us everything about the flow, so these are exactly equivalent. This box down here is the mean velocity. Okay, so this is the thing that governs the skin friction, but you can see from this setup that all these other waves interact to force to give you that mean velocity profile. So this is a pretty complicated diagram, but the essence of what I'm trying to say is that I can think about this flow in terms of traveling waves. And by doing that, I can break this down, and I can consider just one of these blocks at a time. And if I do that, I actually find in my formulation here that it's not as complicated as I would have thought starting from these equations. So I can make an analogy here to trying to understand flow around the body. If I want to understand blood flow, I can either try and model all our veins and arteries, and it would be a very hard problem, or I can say the majority of the flow goes through the largest veins and arteries. If I just understand those, then I'll get pretty close to what's actually going on. So I can do that with these individual transfer functions too. And that was the mathematical simplification that this formulation permits. So if we see how good this analogy is, here, this is analyzing one of these transfer functions, and I call it test tube turbulence, because we can separate out these little boxes now, these transfer functions, and understand how turbulence fits back together. So if I analyze one of these boxes, I can get some statistical results which are quite promising, but the neatest thing that we found is that we can also regenerate these arrays, this is the streamwise direction, arrays of hairpin-like vortices. So here's the sketch I showed you early on. If we start to sum more than one of these little boxes, we can get arrays of these hairpins that appear to grow in space and appear to straddle low-speed velocity regions. So I also showed you an image that implied that before. And that's consistent with the state of the art in the field, which tells us that these hairpin vortices are aligned with low-speed regions, and they form these kind of packets. So it's promising. It's yet to break, this model, in fact. So that's quite good, but you may say, so what? Well, let's go back to the analogy of the body. And if I really wanted to see where the blood was going in the body, then I would tag it. I would put in a tracer. That's probably, I hope there's no doctors in the audience, it's probably a really bad place to put a tracer, but bear with me. So this green blob, I put it in here, and it would travel around the body, and I would be able to see where that blood was going. So I can do this with my little model over here. I can say, if I can override the natural forcing, I can inject something here, then I can see where it goes around this loop. And it allows me to see what the pressure points are that will allow me to change this flow. The way I do that is from the wall, so that little egg box cartoon I showed you is very simple, but it allows me to pick out k, n, omega, this particular combination of parameters, and couple that to what the flow is already wanting to do. So now let me quickly show you how we do some of these experiments. We work in the Merrill laboratory. If you were to go to Guggenheim, the Guggenheim building on the south part of campus, and to go in the doors, you would see the bust of Theodor von Karman, first director of GALCIT. We saw his name mentioned with regard to the mean velocity profile of turbulent flows. And if you went downstairs and more stairs and through some doors, you would find the Merrill Laboratory. And here is a picture of Albert Merrill, for which the laboratory is named. He was a very important figure in the history of Galset. He was one of the first instructors in aeronautics. He brought the first wind tunnel to the west coast, up at PCC as it is now. The neatest thing about Albert Merrill is that he learned to fly with the Wright brothers. This is Wilbur Wright here. So there's a wonderful piece of aeronautical history. So it's an honor to be working in a laboratory with his name on it. So there's the Merrill Lab. So here's if you went in the door, here's what you would see. Well, this is the plan of it. This is the wind tunnel. So the flow goes anti-clockwise around the loop here. There's a fan in this section which drives the flow. And there's a test section 8 feet long right here. This is what it looks like, looking diagonally up. So the fan is behind here, and here's the test section. If we take a look at the test section, here's my flat plate. Remember, be creative. This is not just a flat plate with air over it. And if we look a little closer, we'll see some of the diagnostics that I'll talk about, and that's the view downstream. So we have a plate suspended halfway up this test section. Here's the diagnostic. You can see a laser beam there. It's illuminating some particles which track the motion of the fluid. There are 2 probes here also. One measures pressure, and if you combine an isentropic deceleration of the flow with a measure of the static pressure of the flow, you can get the mean velocity out. That's one of Bernoulli's equations. The second probe is a device we use to measure the instantaneous velocity by heat transfer. So we heat it. The way that it cools gives us an instantaneous, or at least very fast, response measurement of the instantaneous velocity of the flow. Let me talk briefly about particle image velocimetry. So there's illumination of the particles in the flow. If I have a camera that has exposures every 1,000th of a second, and I illuminate those particles in the flow separated by 10/1,000,000th of a second, then I can get a reflection from the particles. So here's the first image, here's the second image. If I track where each particle has gone, so there's a change in the streamwise direction, a change in y, then I can get the velocity in 2 components. So that's what we call particle image velocimetry. Here's another feature of this flow. This is the way we introduce our morphing surface. We do it mechanically right now. So these are 4 little ribs that we can move up and down into the flow. So this is 2-dimensional. The cartoon of the egg box is a little hard for the first experiments. I'll show you some simple results from this. So these are the scales that we introduce to the flow. Here's the schematic. So it's a very short patch of roughness, and we look downstream of this to try and understand the way the flow has responded, to see whether we can excite these modes and do this test tube manipulation. So here's a schematic to orient you to what I'm going to show you. I'm going to show you measurements 3 times this thickness, boundary layer thickness here, 8 and 24 boundary layer thicknesses downstream. And I'm going to break down the velocity into a time mean, a component at the frequency at which I'm actuating the flow, and then the rest of the turbulence. So the physical frequency is 30 hertz, and these elements move 1 millimeter high in a 20 millimeter boundary layer. So about 5% of the boundary layer thickness. Let me show you what we put into the flow. We can get this out by what we call phase locking. So we just average relative to the position of the roughness. So we can average to when the surface is flat and all the way up to when it's fully deployed and down. So what this shows us is exactly the disturbance we're putting into the flow. So hopefully you can see that in the streamwise component, U, and the wall normal component, we're putting something very strong into the flow. U has a very complex shape, but it's persistent to even 24 boundary layer thicknesses downstream. So that's encouraging. We don't need these 20 billion actuators on our A380. And V looks kind of different. That's associated with these ribs going up and down. So red is a fast fluctuation, and blue is slow. Let's look quickly at what happens to the rest of the turbulence. We expected to see something associated with the 30 hertz. But we also see that the rest of the turbulence sees this footprint also from what we're putting in at the wall. So what we're putting in is sort of the puppeteer. It's controlling the rest of the turbulence. So that gives us a bigger footprint, more control over the flow than perhaps you would have anticipated. But it tells us that we're doing pretty well. The acid test is whether we can predict this shape with the modeling that I showed you before. And it turns out that we do pretty well. So let's start with the wall normal component, and you can see that the shapes are really pretty much identical. In terms of the streamwise velocity, we do very well close to the wall. Not so well out here, but we understand why. That's because this roughness is not the ideal way to do this forcing, but the agreement we get close to the wall is very promising. So what? So this gives us a blueprint for getting to skin friction. So I told you that this little transfer function down here controls the mean velocity, and if I don't do any forcing on the flow, I have the red, this turbulent mean profile. This formulation allows me to say, I don't want that, I want the blue one, something close to the laminar profile or something with a reduced skin friction. And I can back out of this what forcing I need to put in at the wall or in another way to sustain that particular profile. So that's pretty powerful. I won't have time to tell you too much about exactly how we do this. Suffice it to say that the fluid mechanics appears to be the hardest part. So I have wonderful colleagues at Caltech who can tell me how to make things like these little very thin metallic films that buckle on demand and would put in this sort of perturbation. So let me wrap up now and say a little bit in conclusion. So have we tamed turbulence? Well, I showed you this mass of intertwangled, that's a new one, isn't it? Intertwined or intertangled vortices associated with a direct numerical simulation. I would say that that's the full untamed turbulence. I've shown you that we've been able to break down turbulence into component parts, put them together, play with them, manipulate them individually, and see how you associate that with the rest of the system. So that's a little bit more friendly, but there's always a little snarl at the end. I hope you've taken away from this talk that turbulence is A, everywhere, and B, a significant drain on our resources, on our environment, and something that we really ought to be able to do something about. But it's hard. I've shown you some of the steps we're taking towards doing that, and hopefully in a few years I'll be able to update you and tell you that we've done it. Let me thank my collaborators here. The model that I showed you is with Dr. Arti Sharma at the University of Sheffield. These are the members of my group who've contributed to the work. Hopefully some of them are around. If you see them, question them hard. And I thank the support from the Air Force Office of Scientific Research, the National Science Foundation, and the Office of Naval Research. So I'll finish there. I'd be really happy to take questions at the podium at the end here now. So thank you for your attention. Have a safe trip home.